We move to the last speaker of this session, Dr. Shibdas. Dr. Shibdas Banerjee is going to talk to us about the alchemy with water microdroplets. Dr. Shibdas.
To the Academy for giving me this wonderful opportunity to talk about our work, and I'll be presenting today something very unusual, apparently, and it can be viewed as almost like a modern alchemy. And this has been enabled by the simple use of two earth-abundant substances. One is water, another is air. And it's nothing but a free-fall droplet, water microdroplet in the air. So alchemy, you know that it's a things happen. So what is it? That I'll take you to the details of it. You know, the water microdroplets are wide in the nature, and it can be sourced from different, the resources, be it natural or anthropogenic. Now, this chemistry in such micron-sized droplet has been the active area of research throughout the century, and it has been transformed from the interest of atmospheric chemistry through the fundamental understanding of aerosol chemistry, surface chemistry, and this water droplet was viewed as a passive carrier, host of atmospheric reactions. But what happened in 2011? So it was found that water microdroplet has a remarkable ability that we observed something very unusual can happen in it. A molecule can be transformed unusually into different molecules. Is not possible by the conventional knowledge of bulk phase chemistry. In the same year, another report appeared from the Graham Cook lab in Purdue University, who declared that the reaction can be dramatically accelerated in micron-sized droplet. And the time when people much talked about the reaction acceleration in the droplet, I joined the laboratory of Richard Zer in Stanford University and found another intriguing process that can happen in droplet is the reaction, chemical reaction can alter its pathway to yield the different compared to the bulk phase process. So these three reports actually mark the beginning of a new era of chemistry. And what happens, what makes droplets so unique? That such very unambiguous things happens. So what is the pointer here? Okay. So we initially thought that it's because of the confinement of small space in the droplet. But later we realized that it's more than that, because the water microdroplet has a chaotic boundary where the water density steeply vanishes within a nanometer distance at the interface. And many organic molecules can on the surface of droplet in a very specific orientation, so that hydrophobic side points to the air side and hydrophobic residues points to the liquid side. And also the partial solvation plays an important role for the reaction to occur at the interface. Then long back, 100 years back, effect. What is that? You never get a droplet neutral in the atmosphere. All are charged droplets. Whenever you generate any droplet, be it in the laboratory or any natural process, this Leonard effect, dynamic charge separation, as well as the dipole orientation of the droplet, electric field in the order of megavolt per centimeter. So all this and that electric field is good enough to promote a reaction of water molecule itself, because it can also make hydroxyl radical from hydroxide anion and liberate electron in the water at the air-water interface. So you have a droplet composed of hydroxyl radical liberated electron. So it can unite both properties, becomes redox active. It can oxidize as well as it can reduce the substances. So another feature is water droplet in the air is unstable because of the rapid evaporation of the surface water. Because of this separation process, it's more than simply removal of the water. All these parameters or influences becomes very prominent or intensified for a reaction to occur at the interface. Lately, our group has found that because of this intensive electric field, the interfacial air can break down and it can cause a corona discharge-like phenomenon on the surface of water droplets. So gradually we are trying to understand what happens at the surface of droplets. I'll take you to our journey in last few years that my group has engaged with a focus in different, of course, centering with air-water interface chemistry, but in the aspect of synthesizing value-added chemicals, pharmaceuticals, materials, CF activation, and fundamental understanding of this interface, as well as reactive intermediate pieces. We can intercept the intermediate pieces from the bulk phase from your reaction vial and stabilize in the droplet for detection. And of course, the inert gas activation, like nitrogen activated. So I'll discuss about those things briefly. So of course, I need to clarify here, it's not just the analytical observation. One can make the material in gram scale also with the right choice of apparatus. So things has moved over time. So people have learned how to make it more preparative from semi-preparative scale. And this is our finding, in the latest finding in a few years back. One is the phenol. Conventional chemistry knowledge teaches you that phenol will dissociate in water to make phenoxide anion. But in droplet, it behaves very anomalously, and in a very different way. It breaks this selectively, this carbon-oxygen bond, makes this phenyl cation. It's very surprising. And also, this process is so exclusively that we typically level this phenol with OH in water, and almost 78 to 80% yield we achieved. So it's very unusual. And another thing is, another precursor, which is benzoic acid, was found to make this phenyl anion water interface, carbon-oxygen bond or carbon-carbon bonds, to make these highly reactive pieces. So then we move to break the strongest organic bond, which is carbon-fluorine bond. It's the strongest organic bond. So then we found that this type of fluoroarine compound is also very unstable at the interface of the droplet surface. And here the mechanism is somewhat different, because the electrons can be injected from water droplet to this heteroarine compound that can make this bond labile to be broken, carbon-fluorine bond, and it progresses through the generation of radical, then cation, and then we could combine. We are detected by high-resolution mass spectrometry technique, which is the workhorse for us to detect these intermediate pieces. And also, the reaction was found to be energetically beneficial. And latest one, although we did not patent it, is the pharmaceutical synthesis in water droplets. So what we found that if you mix indole and amine in water and spray it, aromatic ring through the skeletal rearrangement to the other aromatic ring, and we could synthesize many pharmaceuticals using this approach. Next, we moved from organic to inorganic, and we found that the water droplet or micron-sized droplet containing water has the ability to make this polyoxometallate framework. So if you just simply spray using a spray bottle this tungstate solutions, it will assemble and make the big cluster of polyoxometallate. And the reaction is very instantaneous. Over a millisecond time scale, it gives you 99% yield. Whatever you spray, you get the product. And then we also made this chemistry multifaceted, not only just the addition of bonds or making new molecules for synthesis. We also tamed water droplet to intercept the reactive intermediate pieces from the reaction vial and then seize it there for the spectroscopic detections. So we call it ion fishing process or intermediate fishing process. We can fish out the reactive species through droplet using a droplet, high-speed droplet, and then we can take it out to the gas phase for the detection using mass spectrometry. So we began with detect carbocation intermediate, not stable carbocation, highly unstable carbocation. And then you can see that destabilized carbocation we could also successfully intercepted. And then reactive carbon ion pieces, protein unfolding intermediates. When protein unfolds, we can seize those intermediates using characterize. And then spatiotemporal resolution of reactive pieces that formed in the electrochemical reaction vial or electrolytic cell. And we also evaluated the enzymatic reactions by intercepting or capturing the different intermediate stage in the real time of the reaction. I'm not taking you to the technical details because of the lack of time. And then this study, which published in sometime in 2020, has inspired us. This one is a strong electric field observed at the interface of aqueous microdroplet. It was published by their group from Stanford. And they found that the aqueous interface can have the electric field as high as megavolt per centimeter. It's a huge electric field, megavolt per centimeter. Then this led us to believe that discharge happens because that electric field exceeds the dielectric strength of the air, and that breaks down the air. Then we thought that is similar type of phenomena happening in the droplet surface or at the surface or interface. So based on these two reports, we realized that the dielectric strength required for the air breakdown, which you see in the lightning, is in the order of 3 megavolt per centimeter, and that is good enough to ionize air ions and atomize it, so that oxygen and nitrogen can break down, they can recombine, make the nitrogen oxide bases. So my assumption was that is the similar type of lightning discharge happening on the surface of droplets, and is too feeble to experience. I needed very highly sensitive detectors, and with a series of experiments, we detected this phenomena, similar phenomena like lightning at the sky that can happen at the interface, and we published it in 2024, and it has also a page of analytical chemistry. And later in the literature, this phenomenon has been termed as micro-lightning. So we are the discoverer of this phenomena, micro-lightning effect. Okay, then we can activate the nitrogen, make the nitrogen oxide at the interface. Then led us to believe that if this plasma-like state exists on the surface of water droplet, then why don't we see the activation of argon? Because argon is known as the epitome of inert gas. But my hypothesis was that is that become reactive on this surface because of micro-lightning effect? And yes, indeed we found a very mysterious peak in the mass spec, and if you combine all elements from the periodic table and see what is the mass comprised of which element, you will only end up with argon, because it's a very high resolution spectra. And these peaks only occurs when there is argon, be it air, because argon is the third most abundant gas in the air. And while most of the air gases has been fixed over geological time scale, argon is not known to be fixed. So, and we surprisingly found that this species, which is attributed later to argon hydroxide, and which is generated in presence of argon only, not in presence of nitrogen, and was also well characterized through the isotopic distributions. And we found it has the stability at the interface almost 0.5 second. It's quite stable, 0.5 second stability, 0.5 second. It generates and disappears, again regenerate. So we found that side and hydroxyl radical, this species is also formed OH plus hydroxyl cation that can combine with argon and make the argon hydroxide cation. And this species looks like this with a theoretical support, and the reaction is exothermic once you get the OH plus. So summary of because I have not presented all our work, but some we handpicked. The summary of the work is microdroplet can render a catalyst-free and reagent-free approach for molecular synthesis, and it can be viewed almost like a modern alchemy, and it's metaphorical, pardon me, just by the use of water and air. And alchemy sought transformation through mystery, and microdroplet chemistry achieves it through interfacial physics and chemistry. So being associated from the early stage of this chemistry, so what I can view for this field, it can take us long because it's catalyst-free, reagent-free, and also benign solvent you use like water. So we are reaching to the era of a truly, the green chemistry, where all you need is air and water to make the transformation. And thank you for your patience. I'll now invite for the questions. And I'm thankful to these students who are the driving force for all this work. And some of them are here, Avijit and Anubhav. And others, I have another group who are working on disease diagnosis. I have not discussed about that. And I have a wonderful theoretical collaborator, Debashish, from IIT Hyderabad, who supported us with theory. Thank you.
Yeah, let us thank Dr. Shibdas for a very exciting presentation. We can have few questions.
Debashish, congratulations. Quick question.
Okay.
Where do you think it's lie the translational value, either in the area of biology, medicine, or forensic science?
So we mostly see the molecular transformation. It doesn't matter where it is.
No.
We
That
did-
you have shown beautifully,
Yes.
and I appreciate.
Right.
My question is very simple. Can you find its application either in the field of biology, medicine, forensic
Yeah,
science?
the pharmaceuticals
That
we-
means it's translational.
Right. Pharmaceutical we have synthesized. This is the beginning of the work. Of course, more work is needed. Answer you another 10, 20 years for us.
You have some
Where will lead us?
metabolites detection, all
Okay.
that. You are not looking at that application? In
Application
medicine?
we are looking. We are working with materials. We are working with the pharmaceuticals. We are working with fine chemicals. And of course, another thing is coming. We synthesize biofuels using droplet. We have not published it yet. It's under peer review. Biofuels, precursor of biofuels from the organic materials.
I have a very simple question. The water droplets, microdroplets that you're generating, do they have a fixed charge? Fixed charge meaning positive only or negative?
It's on
only?
demand.
And what is the distribution of the charge?
Exactly. Okay. So if you need to make it charge, you can charge. You can apply an external potential to make it charge. You use the electrohydrodynamic spray process.
Is it charged all the time? Or is
All
it
the time it's charged. And also, as I mentioned, no droplet in the air, you get neutral. Even the droplet travels through the air because of the electric field generated at the interface for dipole orientation. It can ionize the air molecule that I have shown, the micro-lightning effect. Practically, you won't get any droplet neutral.
Okay. One small question. Is it possible to rotate these microdroplets?
It's a high-speed
Give them
droplet.
an angular momentum?
Yes. It's a high-speed droplet.
In a controlled way?
Yes. It's a high-speed droplet. You can control it. You can also control the size of it. Like whatever you want, you control the speed of it using a spray parameters.
So my question is more naive question. What are the possibilities in long run from water and air we can actually develop our food component, nutrition?
Yes.
Possible?
I cannot assure you without experiment, but many possibilities are there because given the field is evolving.
Thanks for a fascinating talk. I go for a walk in the beach in the evening in Chennai. Sometimes when there is no moonlight and when it's dark, when the waves break, I see brightness. People say it's chemiluminescence of this
Yes.
some.
Yes, because
But-
sometimes methanes are developed.
So is it with the phenomena that you are
Yes,
talking? Is it happening
micro-lightning.
there?
Yes. Absolutely. Studied through this phenomenon from their lab from Stanford. They found that this type of chemoluminescence appears because of the micro-lightning effect.
Thank you.
Yeah.
So while doing ESIMS, can the
Some bit of it, if it is not too much, some bit of it can convert. That is how you see the background signals in the spectrum that appears from the fragmentation or transformation of these molecules.
Shibdas, excellent lecture. I must congratulate you. But I have a small doubt that recently I read some papers from Zayer's lab where he says it is a size-dependent phenomena of the microdroplets.
Of course, size dependent.
So what happens at the nanoparticles, it doesn't work. Only in between range of the micro.
If it is too small, because see, organic molecule also has some certain size. If the droplet is too small in the range below nano, the electrical double layers and all these things, that play a crucial role. But that's below 100 micron, this chemistry is observed. Above 100 micron, more or less, it behaves like a bulk.
That's right. So
Yeah,
above
that size.
100 micron, it's bulk, but
Right.
nano also it is bulk.
Nano is not like a bulk, but the thing is that because of the development of electrical double layer, it becomes more redox active. So, for example, whenever you are nebulizing anything, directly you do not land it into the nanosafe. you bring it gradually from macro to micro to nano. But most of the chemistry, what we believe to occur in the micro diameter, But once it lands to the nano, which generally we determine for mass spec study, remains more or less in the micron level, which has been seen in the high resolution camera also.
Thank Dr. Shibdas for a very exciting presentation.